We've looked at probability distributions where the outcome of a random variable can take specified values, discrete values. But now what if that random variable takes values which is continuous data? For example, height. We have to treat things slightly differently. So for continuous outcomes, we look at this with an example. So a metro station in LA, trains arrive exactly every 15 minutes. You don't know when the trains arrive, you just know they're every 15 minutes. So you just arrive at a completely random time, knowing that at the most you'll have to wait 15 minutes if you've arrived just after trains left. You want to know what is the probability that you'll have to wait exactly 5 minutes. Now if we were to treat this like a discrete variable, we would go the probability of waiting exactly 5 minutes is the size of the set of all the outcomes I care about divided by the size of set of all possible outcomes. I care about one time, exactly 5 minutes, and I want to divide that by the number of all possible outcomes, all possible waiting times. But because this is continuous data, there's actually an infinite amount of possible waiting times. I can be waiting 5 minutes, but I can be waiting 5.5 minutes, 5 1/3 minutes, 5 1/3 and a bit minutes, and so on. So with continuous outcomes, it just doesn't make sense to ask what's the probability of getting an exact value, one exact value out of all the possible continuous outcomes. So we have to think about things differently. Instead, let's ask, what is the probability that I will wait less than 5 minutes? Now I can do the same sort of thing. Probability of me waiting less than 5 minutes is the size of the set of outcomes I care about, all the waiting times less than 5 minutes, divided by the set of all possible outcomes. That is infinity divided by infinity, which of course doesn't make sense. But I know something about the ratio there. Because I know everything's equally likely, 5 minutes is 1/3 of 15 minutes. What I'm doing there is I'm comparing the ratios of two uncountable sets. More formally, we can calculate stuff like this using what we call a probability density function. And this is different to a probability mass function that we looked at before, because we are now looking at continuous data. So for the scenario I looked at, waiting time, where I can wait anything between 0 and 15 minutes, all equally likely, this would be my probability density function, and I've plotted it on a graph. As they're all equally likely, I can just draw a flat line between 0 and 15. I haven't told you what the scale is yet. That flat line does not represent probability, but it does represent some sort of measure of how likely something is. What does represent probability is the area under that graph. Now in this case, we can work out what the height of that line is. The area under the graph is probability, and I know that I must be waiting somewhere between 0 and 15 minutes. I can't wait less than 0 minutes, and I can't wait more than 15 minutes because a train would have come in that time. So if that represents my whole sample space, that area is 1. That's a rectangle in this case, and I know one of the sides has length 15. If the area is 1, then the height must be 1/15. But that's not always the case when we get some probability density functions which are not straight lines. And then what we were saying by asking what is the probability of me waiting less than 5 minutes, I was just looking at the sample space between 0 and 5 minutes and asking what's the area under that curve now? Probability of my random variable x being less than 5 minutes is the area under the curve between 0 and 5. I could have asked other things. I could have asked, was the probability of me waiting more than 9 minutes? And that would have been the area under the curve between the values 9 all the way up to the 15. And I could have asked, what's the probability of me waiting between 2 and 10 minutes? And the same logic applies. Like I said, these probability density functions, PDFs for short, don't have to be a flat line. more than likely they're going to have some form of curve. Here's a very common curve you will see. This is actually called the normal curve, and we'll look more on normal curves in another video. But the same logic applies. Now if we've got some outcome where the value can take something, roughly between 140 and 120, this PDF is a measure of how likely something is, but it's not probability, which means I'm more likely to be around the 180 area than I am around the 140 area. And if I want to be precise, the probability of my outcome being between two values, so here be between 145 and 182, is the area under that curve between x equals 145 and x equals 182. Now, in order to work out that area under the curve, we need calculus. And we're not going to go into that in this module, but we will look at the normal distribution further, and we will look at other ways of working out the area under the curve for the normal distribution. These PDFs, they're very useful, but they're not that readable. A much more readable function would be the CDF, or the cumulative distribution function. And this maps a numerical outcome x to not the probability of x being equal to x, because that doesn't make sense, but to the probability of x being less than or equal to x. For example, look at our waiting time for trains in LA before. This was all outcomes were equally likely, and this was the PDF. Now that's actually called a special name. That's called the uniform distribution. But in order to read probabilities from that, we need the area under the graph. The CDF of this, however, is this. And now the y-axis is probability, and the x-axis is the value of the outcome. But the y-axis now is probability of having that outcome or less. So now that line, we don't need to look at area under the curve anymore. That line itself gives us an interpretable probability. This x value here, outcome of x, the probability of having that value or less, any of these, is this probability value. We're going to look at some more useful named distributions now, and we're going to look at their CDF. So a very useful distribution is the exponential distribution. And the exponential distribution is used a lot to describe things randomly across time. So if things are truly randomly spaced across time, then the times between each of those events comes from an exponential distribution. Let's have a look at what the CDF would look like now. The CDF would look like this. Being able to convert from one to the other in your head, or just roughly what that would look like, is a useful skill to have. So we can see here, as our x value increases, the more area under the curve we're adding decreases. So the CDF, it's always increasing because we're always adding more stuff, but the rate of change of it decreases. Another distribution which is useful for describing things is called a bathtub curve. And this bathtub curve, for example, is really good at describing the age of death of humans. If the x-axis goes from being born 0 to very old, 100, then we are much more likely to die when we are babies due to complications, and we are much more likely to die when we are older. We are much less likely to die in our middle ages. The corresponding CDF of this then, see if you can think yourselves what it would look like. But it would look like this. At the start, as we're increasing x, we're adding less and less things every time. So it sort of gradually levels off. But then once we pass this middle area, as we increase x, we're adding more and more things every time. So the steepness increases. Not all distributions are going to follow something really Nice. Sometimes we get something called bimodal distributions. In a bimodal distribution, think about the name, two mods, so two most likely values, which of course doesn't make sense for continuous data, but you can see in this example we have two peaks. So a peak is roughly where do most of the values lie, and we've got two areas where roughly a lot of those values lie. So it's kind of two modes. So that's why we call them bimodal. This would describe, for example, maybe the heights of two very different populations, the heights of dogs and the height of cats, for instance. Try again now to see if you can work out what the CDF would look like. The CDF would look something like this. As we go over this bump, we get that classic S curve, but then we get another bump, so we get another classic S curve on top of that.